and his primary area of investigation is biomedical image processing. He is internationally recognized for his research contributions to sampling theory, wavelets, the use of spline for image processing, stochastic processes, and computational bioimaging. He has published over 350 journals papers on those topics, and he is the author with Puya Tafti of the book An Introduction to Sparse Stochastic Processes, published in Cambridge University Press in 2014. From 1985 to 1997, he was with the Biomedical Engineering and Instrumentation Program from the NIH, where he conducted research in bioimaging. Dr. Unser has served on the editorial boards of most of the primary journals in his fields, including the IEEE transaction on medical imaging, on image processing, the proceedings of IEEE, and Cyan Journal of Imaging Sciences. He is the founding chair of the Technical Committee on Bioimaging and Signal Processing of the IEEE Signal Processing Society. Professor Unser is also a fellow of the IEEE since 1999, an ReLU fellow since 2009, and a member of the Swiss Academy of Engineering Sciences. He is a recipient of several international prizes, including 5 IEEE SPS Best Paper Awards, 2 Technical Achievements Awards from IEEE, the Technical Achievement Award from RASIP, and the recent Career Achievement Awards from IEEE MBS in 2020. So Michael, we are glad to welcome you and to listen to your talk entitled Splines on Imaging from Compressed Sensing to Neural Nets. The floor is yours.
Okay, so thank you very much, Philippe, and thank you to Charles and Bertrand also for this kind invitation. It's a pleasure to be here. And so you see my title somehow follows the trend in signal processing, because people like Philippe, we were doing compressed sensing and probably now doing neural networks. And since I've always been doing splines, so they're still here, and imaging as well. But I will show you it's more than just a title. Actually, there's a deep connection in the background. So the context here is really like computational imaging, so which means image reconstruction. And just to set the scene, for example, here you want to do microscopy, fluorescence microscopy. You get measurements that are blurred. And so you have a good understanding of the physics, which you model by this matrix H. And there's measurement noise. And of course, the goal there is to invert the process and recover S. And so traditionally in the field, we have formulated this as an optimization problem. So where we impose some data consistency. So we want to pull out a solution that is sort of consistent so that the data fidelity error is small. But this, since the problems often are very ill-posed, there's lots of noise, we want also to regularize the solution, so impose some good properties on the solution. Now, if we look back in the 20th century, what was the approach of solving ill-posed problems? And I mean, this is still like used, for example, in medical scanners, because it leads to linear reconstruction. So typically what you do, you impose some energy functionals that measures how bad your solution is, and so the regularization operator, for example, you use the gradient, you use the L2 norm, and then what you're trying to do, you're trying to guess a solution that's within a certain margin of tolerance with respect to your measurements, and now among all acceptable solution, you try to find the one that minimizes the energy. Now, using Lagrange multipliers, you can rewrite it like that. And so here, everything is quadratic. So you can solve it in closed form, and then you get that equation. So now here, the main point is that this is linear. And now, if you put this in red, which is a matrix operation, and you call it filtered, and this is the H transpose, so that's actually the back projection. So this gives you the very famous filtered back projection, actually, which exists in almost any imaging modality. Okay, now this actually is very similar to learning. And traditionally in machine learning, in fact, you also have an inverse problem, but in fact, it's infinite dimensional because you're really trying to find a function that maps an input onto some output. So typically you will have a bunch of points. So think of the x as your feature vectors, the y's as the desired output. And now you want to find a function so that will sort of map those x into the y's. So you want to find a function such as f of x for every data point gives you something that is close to the desired output. So that's really a regression problem. And then early on, of course, people realize, well, this is super ill-posed because we have finite data, but we're looking for a function which is an infinite dimensional entity. And so what you're doing here, you do the same thing with an operator L, but because we're in the continuum, now we'll put an operator acting on functions, and then we can compute some energy. And then you can exactly frame it as the Tikhonov problem. And again, using Lagrange multipliers, you write it like that. So it's exactly the same thing, just f now is in the continuum. Now this can be solved if the regularization energy is a so-called Hilbertian norm associated with a reproducing kernel, Hilbert space. And in fact, this gives us a kernel estimator, let's say sums of Gaussians, and which are at the very heart of all traditional machine learning, support vector machines, etc. So that's sort of very traditional. Okay, now, okay, a connection with compressed sensing first. So we were involved in compressed sensing, but you know, a little like this machine learning being a continuous business. So we thought, okay, can we formulate a continuous theory of sparsity? And you know, the title of my talk tells you the story, because yes, in fact, there are splines that could be put to good use, and good use, and in fact, they go back to 75, so it's pretty old. Unknown work, we generalized, you know, for much wider range of problems. That's what I'm going to present to you now. So what are splines? I think you have seen my talk, so probably you know. But the splines are analog entities, so functions, but they're intrinsically sparse. And so there's a sort of higher level of defining splines, because you can associate a different type of given type of splines to an operator, a differential operator. And so we will say that the function now that goes from RD to R, possibly growing, is a non-uniform L spline. So here, node L goes with this differential operator with some knots. If now something strange happens, you apply the operator to the spline, take a derivative, okay? So let's say you apply the derivative to your function, and what comes out? A stream of Diracs, okay? And so here, linear combination of Diracs. So the position of the Diracs are the knots of the splines, and so the AKs are somehow the size of the discontinuities. And maybe just to show you how it works, here's a piecewise constant function. So that's a spline of degree 0, but also known as a D-spline, because the operator L is the derivative. Now, if I differentiate, I get 0. Here, of course, I have to ask Mr. Schwarz, okay, so that I'm allowed to differentiate in the sense of distribution. So I get the Dirac. The height is exactly AK here. And then here I differentiate again, I get the Dirac. Everywhere else I get 0. So you see that the piecewise constant function is actually a D-spline, okay, D being the derivative. And we call that the spline innovation, because in some sense it contains all the information of the spline. And then, okay, then we can play a trick to do spline synthesis. So we use the operator, and splines become interesting when the operator has a null space. Otherwise, it's too easy, okay? And maybe not so good. So we like cases where there's a null space. So derivative is perfect because the null space are just the constants. So it's dimension 1. Then we have the innovation here, which is just our linear combination of Diracs, you know, the xk being whatever. And then you try to invert the equation, okay? Because we have ls equal w. W is here, so you need to apply L minus 1. And so how do we do L minus 1? There we use the trick of physicists. So there's something called the Green's function of an operator. And for signal processing guys, you just say, okay, it's the impulse response of the inverse operator. So what is the inverse operator of the derivative? Is the integrator. If you teach signals in system, you know that the impulse response of the integrator is the heavy side, okay, the unit step. And then it's easy. Actually, what you do, you just replace every Dirac by a unit step. And if you add up everything, you get a piecewise constant function. Of course, there's a little caveat here, because all this is not completely well defined. You still need to give a boundary condition because you have a null space. Okay, so then there will be here a component that can be in the null space plus just a sum of heaviside functions. Now you can do that much more general. So use any LSI, linear shift invariant operator. So we call spline-admissible. So that's when you can compute splines. And that's important. You need finite dimensional null space, possibly trivial. Okay, so if it's really easy, it could just be just zero in the null space. But here we allow, for example, the null space being finite dimensional, composed of polynomials typically. And then what we want is a Green's function. And so the Green's function should be the impulse response of the inverse filter. And there, again, okay, I'm a great fan of Sparse. Okay, you really need distribution theory because usually, you know, those impulse response you can compute by inverse Fourier transformation, but of course using the generalized Fourier transform in the sense of Sparse. Okay, so you know this Green's function and you want it to be an ordinary function. So that should not be a distribution, it should just be a nice function that you can draw. And then again, you go back to the innovation and you play the same trick. So now you just replace the Dirac, not by the heavy side, but by the Green's function. So now it's very general because it works for any operator and that has those properties. And don't forget to put the component in the null space. For example, here, piecewise linear. So this goes with D2. Okay, so double integration, because if you integrate again the heavy side, you get the ramp or the ReLU. Okay, and don't forget the boundary conditions. So then, okay, to go a little further, we need a proper continuous counterpart of L1. And so there people have mistakenly thought this is the space L1, capital L1. And in fact, it's not. You need a more sophisticated space. That's the space of bounded radon measures. So here's Johann Radon. And the way to define it properly, you define it as the topological dual of the space C0. So the space C0 is the space of continuous functions that are bounded and that decay at infinite. And then we can also, you see here the definition of the M norm. It's a little like the dual of the L infinite norm, because you have L infinite here, but there's a constraint, okay? The function should also be continuous. Actually, you can even use a function in Schwarz's class S, so that's smooth and infinitely differentiable, because this function space is actually dense in C0. So that gives you a clean definition of the radon, bounded radon measures. And now, okay, for engineers, it's not very intuitive. So engineers know L1 functions. So the good news, if you're in L1, you are in M. And actually the M norm, which looks very complicated, is actually the same as the L1 norm that you all know. But what's important is the Dirac lives in M. It doesn't live in L1. Okay, and Dirac is super important for us. And so here comes our theorem, which I call the representer theorem for generalized total variation regularization. So here we have an operator that's spline-admissible. We have this M norm. We have measurement functionals that can be anything you want. It's just a linear inverse problem. The only thing is those guys should be continuous, okay, which for mathematicians is really the minimum requirement. So then you look at this problem here, data term, regularization M norm, okay, then, okay, you optimize over this Banach space here. And what you get, wow, I'm super happy. I mean, when I found that, I was, wow, okay. The solution of all those problems, whatever the imaging is, if it's MRI, microscopy or whatever, it's always a spline. Actually, it's not only a spline, because the solution in general is not unique. So you have a convex set, and there's something that's called the extreme points of the convex set. Now, the theorem says that every extreme point is a spline. And it also says that it has less knots than the number of measurements, but it doesn't tell you where the knots are. It doesn't tell you how many there are. So that's part of the optimization. And then, of course, you can make that more general. The data term, you can put anything convex, and it's the same story. So maybe here, take-home message, if you have a generalized linear inverse problem, and if you use that regularization, the solution is always a spline. Okay, good news. So then let's go back to supervised learning, because we're talking about AI. Okay, so let's just borrow the M norm for supervised learning. So that's okay, data fidelity, M norm of second derivative. Now here okay, it's a particular case. Here is just the H here being a Dirac, okay, at the location of data point, and that's actually weak star continuous. So then actually the solution exists. Then you have this TV2, which is the M norm of the second derivative. So what it will favor is sparse second derivatives. And generic form of the solution, you look at the Green's function of D2, and it is ReLU. Okay, so the solution of that problem is just a linear combination of ReLU. And so you could say, yeah, it's a neural network with one layer, one layer, and actually a linear spline. Other spline-admissible operators, so it works for any derivative, it works for any ordinary differential equation operator. You can go for fractional derivative, it also works. You can use fractional Laplacians if you want to go to higher dimension, it also works. Actually, you can also use those guys, and those guys are used a lot so there's elliptical differential operators that are used in the theory of Sobolev spaces, and so those gives us Sobolev splines that are sums of Bessel potentials, but exactly with the same formalism. Okay, so you say, yeah, that's nice math, but what can we do with it? Of course, we can do compressed sensing. So we can now try to discretize. So discretization, remember LS in the continuous domain should be sparse. Okay, so now we can discretize all this, and now this thing we call the innovation, and we discretize, and then we can also use augmented Lagrange multipliers. Write it like that. So I'm going very fast because this is, let's say, last decade stuff of compressed sensing. And then you can write it like this, use ADMM, augmented Lagrangian. So you have some auxiliary variables, that's the innovation, the Lagrange parameter. And then you can solve that problem iteratively. First, you assume U and alpha are constant. You solve the problem. Now, good news. It's exactly the same form as Tikhonov. Okay, it's a linear solver. Then you update the Lagrange parameter, and then you solve that problem, which it's just a denoising problem. And I guess if you know compressed sensing, you know that this proximal operator here is just a soft threshold. If you iterate, you can solve your problem. And this is very nice because you can just borrow a very fast solver of the 20th century that does, let's say, filtered back projection, and just use it iteratively, and you will implement compressed sensing. So we did that many years ago, also in MRI. So at that time with Prusman. This is just an old illustration, but it illustrates like if we do subsampling in K-space, we get some aliasing artifacts. If we use a conventional reconstruction, if you use TV, you can get rid of those. And there's lots of activity, of course, taking place in compressed sensing. And I will not tell you much more because I think AI, you're interested in deep learning, okay? So let's switch to deep learning, and you'll see there's a good connection. So now, if you look at this algorithm, okay, now what you see is actually an iteration between something linear and nonlinear, and it's even pointwise nonlinear. So if you unroll it, I mean, if you unroll it, you have the structure of neural network. But people also talk of convolution neural network. So then we can see, when is that thing here a convolution? And actually, there are many cases where it's a convolution. It's maybe not always so well known. Of course, if you have deconvolution problem, this linear step is a convolution. Now, if you have computer tomography with parallel rays, this is maybe not so well known, but this guy also is a convolution. And now if you have MRI with non-uniform case space sampling, this guy is also a convolution. Okay, and so therefore it's convolution followed by nonlinearity, convolution, nonlinearity. So it really looks like a neural network. And of course, this was the idea of Lequin, Gregor. They actually used in the early days also neural networks to actually emulate the kind of algorithms we were using in imaging to do compressed sensing. But then, of course, was the idea, yeah, okay, I mean, the ADMM uses fixed weights, so why can't we do it better by learning? And of course, I mean, there were many people who had that idea at more or less the same time, probably Philippe, Charles, and Bertrand as well. I don't know, but anyway, so I had a very good postdoc in my lab, so it's Kyong, and he said, okay, it's nice your math, but you know, I heard that neural networks are really cool. I want to use neural networks to do image reconstruction. And so then you also thought like it's a good way to apply them in the compressed sensing scenario. Why? Because actually we need a gold standard to train the system. So let's say we can take few measurements and train it, then reconstruct with whatever algorithm. So you get lots of artifacts, and then train the neural network to correct the artifacts by regressing them with respect to a high quality reconstruction. And he used UNet type architecture. And actually the results were amazing. So here's the ground truth. Here's like, and here we have a dose reduction by 7. So it's, you know, quite something. So here's a filtered back projection, let's say Tikhonov. Here is the, let's say, early last decade type of compressed sensing algorithm with total variation regularization. So you see, we had 10 years of compressed sensing. We gained roughly 5 dBs, okay, which is very nice theory. And then come compressed, neural network, no theory, puff, another 5 dB right away. Okay, so I can tell you this really depressed lots of people in my lab. Okay, but I mean, we were persistent. We wrote it up. We published it at the right time, and actually this had quite some success. In fact, oops, you know, it earned us a best paper award of IEEE. By the way, I mean, I like the paper. There's a, even though it's a neural network, there's a theorem in the paper, so it's not just experimental. Okay, so this, okay, then it works. I mean, those are other type of tomography with 20 times reduction of the dose. So here you start having all kinds of artifacts. Of course, you can use total variation, but you wipe out details. You use filtered back, this, you know, neural networks, and that makes it work a little better, okay? And certainly in terms of signal to noise ratio. Okay, so now let's say there's this disconnect. We have the nice theory, we have neural networks, and neural networks beats the nice theory, okay? So you're a little depressed, but you don't understand what those neural networks do. Okay, now here's my message. If there's a take-home message, don't worry, because neural networks are splines. Okay, and that's what I want to to develop now. Okay, so splines, I mean this guy. Okay, in 1D, So this wise is piecewise linear and continuous. Okay, so this guy is a non-uniform spline of degree 1, as we saw. So we have many ways of defining such a function. So first of all, we can first define the partition of the real axis, puts the knots. So the interval between two knots, okay, that's refers to those pKs. Then, okay, we say that the function now is piecewise linear and continuous, okay, or spline of degree 1. If, first of all, in every interval, it is linear, so that's just the equation of a straight line, like here. But this is the easy part, okay? The hard part is the second condition. It should be also linear in the other interval, but the guys should join, okay? There should not be a discontinuity. They must join, okay? So this is the very, very hard part in constructing the spline. So if you have the two, you have a spline. And then you can either represent it like this, which is the way, let's say, I just used there, a continuous piecewise linear, or maybe a smarter way, because it's very hard to impose the continuity. Now, if you use basis functions that are already splines, like the ReLU, so then it's a no-brainer. You just have to do a linear combination of splines, you get splines, okay? Now, okay, then there's, how does that relate to the theorem that I just presented to you? Actually, splines are very old. I mean, they're 60s, 70 years old. Now, here's a problem for you. How do you interpolate those points? Okay, that's the traditional solution. Debord, 1966, you see, you minimize the L2 norm. It's like in my second slide and Tikhonov. This is just the continuous domain counterpart. So here we have the derivative and the energy of the derivative. And if you do the math, you find this. Okay, now I showed you another theorem, the sparse version of that. And that's not obvious. Now I ask you, can you find a sparse interpolant of this? Here it is, okay? So we put the M norm. Now we use the second derivative M norm, same thing here. And now, okay, you see here what happens. It's also piecewise linear, but the knots is not on the data points necessarily. And here there's just one, okay? It's much fewer than in the other case. And actually, in that case, you have possibly infinite solutions. But you have, in that case, you have one that has minimum number of knots. Okay, so among the infinity, there's the best one that has the sparsest and the minimum number of knots. And by the way, if you're interested, we have an algorithm. It's on the web. It's a paper where we can compute exactly the minimum number of knots solution. Okay, characterize it exactly. So this is Debar 2020. Okay, now let's go to higher dimensions. Okay, because you could say, yeah, okay, Unser, you stay in 1D, but come on, deep neural network. Okay, we have higher dimensions, so we can do that business in higher dimension. So you can also define continuous piecewise linear functions. So you will partition your domain now in polytopes or simplices like before. And now you say it's continuous piecewise linear if in every polytope or simplex, the thing is linear. So now it's just, vectorial version of a straight line. And now the hard part, of course, is also imposing that the pieces are joined together so that everything is continuous. And now how do you do a multivariate function? Multi-component, I mean, it's continuous piecewise linear if every component is continuous piecewise linear. Okay, so what is the relation with neural networks? Okay, here's a neural network. And you all know that neural networks, so they're neurons. The neurons, they do pointwise nonlinearities, typically ReLU. And then the arrows are linear operation. And so you can represent the neural network as a composition of linear, pointwise, nonlinear, linear etc. Now, there's an enabling property, and there's an algebra of continuous piecewise linear function. This is amazing. If you compose two continuous piecewise linear functions, you get something that is continuous piecewise linear. Okay, so actually this means now the neurons, or let's say the linear step, okay? Linear step is affine, so it's trivially continuous piecewise linear. Now, every neuron is a ReLU, so it's continuous piecewise linear. So if I compose the things, I'm always continuous piecewise linear. And so it means actually that the whole mapping that's implemented by the neural network is continuous piecewise linear. Okay? And actually the property still remains true if you replace the ReLUs by linear splines. Okay, because linear splines are continuous piecewise linear. So I'm not making it up. Okay, it's very ReLU networks are state-of-the-art, and so I'm just saying state-of-the-art neural networks actually are splines. Okay, high-dimensional splines. Now, how can you use our theory? Actually, our theory, we can use it in the following way. We can study the limit behavior of a neural network if it has an infinite number of neurons. Okay, so here's a very simple neural network. So it's written here. So you have the V's here, the W's here, the V's here. And so here's the kind of cost function that people usually apply. So they have, let's say, some data term, and they usually use what's called weight decay. So L2 norm of the weights of the neuron. And then actually, what one can show by using just the theorem, our theorem, in fact, and so that was noted by Paris and Novak. Just by applying our theorem, actually, you can show that actually, that the kind of splines I described to you actually minimizes this problem. Okay, and the spline, the sparsest one, so you allow for infinite number of neurons, but actually it will find the most economical solution that uses the minimum number of neurons. It's not too hard to show. I mean, you can show that essentially. You can exchange weighting between V and W, and you can show that actually the optimum for the weight decay is when W equal V. And then you can show that actually this cost function is equivalent to the total variation I was using in our theory. Okay, so that then, so there's an interesting link here, just let's say with, univariate, two-layer neural network, because at least now this we completely know, because we have characterized the solution in function space, and we know how to get the sparsest architecture that will exactly do that. But now let's do a little more, okay? Now I just told you, yeah, okay, neural networks are nice. Everyone uses a ReLU or something, as activation. Let's be a little daring. Okay, why don't we allow actually our neurons to be anything? Okay, not just ReLUs. Let's learn the neurons as well. Okay, we learn the neurons. So every neuron can be a function to be learned. Okay, I don't tell you how you learn it, but okay, so then you have linear, non-linear, where you learn the neuron, linear, non-linear, etc. And now the problem is, can you jointly train and learn, the neurons and the weights? And now, of course, if you put it like that, it's impossible for the same reason as in the beginning of my talk, because it's completely ill-posed. You have finite data, you're trying to learn functions, neurons that are infinitely dimensional. So you need penalty, okay? You need to regularize. And I think now you can almost guess what I'm going to use. If you weren't sleeping in the first part of the talk, I should not penalize simple solutions because, linear classifiers, they are like the grandfather of machine learning. You should impose differentiability because we train using backpropagation. we should favor simple solution because ReLU, for example, we know it works well. So sparse second derivative. And I think you will not be surprised that I'm using actually the M norm of the second derivative, okay? It's really the perfect regularization for that problem. And then here comes the theorem. It looks a little complicated, but essentially the story is like that. So we're not only training the weights, okay? So I'm just normalizing my weights so that it's not too slippery, okay? But this is just, to make it a little more unique. And then I'm training every neuron. And so now I'm using any cost function that people use for training neural networks. So here it can be quadratic loss, or Kullback-Leibniz, whatever you want. Here, whatever you want on the weights, for example, weight decay. And then I'm just adding here the sum of the total variation of every neuron, okay? And so then what does the theorem says? It said, hey, Michael will be happy, okay? The solution is that every neuron should be a spline. Okay, so you say, okay, wow, cool. But it doesn't tell you how you find it, okay? So sorry. But it tells you that optimality is achieved by choosing neurons that are actually linear splines. Now, the outcome is really that every neuron now should be characterized by some number of knots. You don't know how many. You just know that if you put a strong lambda, strong regularization, there will be few knots, fewer than data points. Then you need to know the location of the knots. So those are like the bias in ReLU networks. And then, of course, there are some coefficients. And okay, note one difference with ReLU. Here it's also adding a linear term, which is very important because it maintains compatibility with classical world. Okay, and then the last thing, icing on the cake, is actually the weights in front of the ReLUs. If you take their L1 norm, that gives you exactly the total variation. So you really have a link with discrete L1 optimization. And then, okay, so the outcome here, globality is achieved by spline activations. And in particular, ReLU network. So for example, Lequin, Benjo Hinton in 2015, they say, yeah, ReLU are really good, they're easy to train, etc. But they're certainly part of the story of the theorem because they're the simplest spline, just one knot. Linear regression, don't forget Gauss, is also part of the story because if you put lambda go to infinite, actually the guy that has no penalties, everyone is linear, and then the whole neural network will collapse to a linear regression. And state-of-the-art parametric ReLU, so it's a ReLU with a linear term that had been proposed some years ago. It's also part of the story. It's also known to work a little better than ReLU. And there's even some not so known work, but of people who propose like putting a fixed linear combination of ReLUs, and they also demonstrated some improvement. Okay, so that essentially gets me to the end. So what I really introduced here is a continuous domain formulation of compressed sensing, but I related it also to machine learning. And so the good news, if you put this GTV, you always get the spline. And what's amazing now, the knots of the spline become adaptive. And there's a direct link in terms of algorithms with L1 minimization. Now, if you do machine learning, traditional kernel methods are closely related to splines. In fact, the machine learning people, they copied the math of the spline guys because Debord was there before the kernel guys of machine learning. So it's more or less the same math of reproducing kernel Hilbert space. So let's say the Tikhonov quadratic world, in some sense, this represents the traditional work framework of machine learning. Sparse variant offer interesting perspective. Now, ReLU, actually, they work really nice, ReLU networks, but in fact, they're high-dimensional splines. And now, at least if you look at shallow networks, everything is explained by spline theory, including the fact that with weight decay, you tend to minimize the number of neurons. Free-form activation, you also have a link with deep splines. And there, I'd like to thank the people in my team. So there are many who helped me, not only on the practical side, the theoretical side. Maybe for those who are interested, we have a paper that came out relatively recently in, I think, Open Journal of Signal Processing, where we actually have an algorithm, now an implementation of deep splines. Okay, so it's what's said by the theorem. So, and it's very efficient. It only costs essentially twice the cost of a ReLU network. So it's twice as costly to train and twice as costly to deploy. Okay, but twice is nothing. Okay, and it's more sophisticated because we have much better activation. And actually, the niche for those kind of architectures is more like for more shallow network, because we have found that in many applications you need to control the Lipschitz regularity of the neural network, and it's much easier when you have shallow networks, not too deep. I mean, maybe 2 layers is too shallow, but let's say 4 or 5 layers. If you start putting layers and layers, you don't understand what's going on anymore. So I would say our framework gives you better performance when you have shallow networks. And so I have to thank ERC. And so those I was telling Philippe, this is my ongoing ERC, but you know, I was among the lucky Swiss to get a new ERC that's called actually FunLearn. And it's exactly about studying what I presented to you a little more, okay? And I must say, yeah, you know, because now Switzerland unfortunately got kicked out of ERC, but they still signed the contract for mine, so I'm still safe. Otherwise, I would have migrated to France maybe, but anyway, that's another story. And here are references. So this is for the solution, no, the sparse adaptive things. Then we have also relatively high-level mathematics that sort of explains this kind of construction. And finally, here's on implementation. And okay, maybe I didn't put everything, but okay, no, the implementation is more here. So like, where is it? Yeah, anyway. So thank you very much, and I'm open to questions, and sorry for stepping over a little.
Thank you, Michael, for this journey in